The goal: detect the earliest index where the prefix sum repeats. That immediately identifies a zero-sum subarray. We will visualize the mathematics, prove why it works, and show how to handle 64-bit overflows safely. Definition: for an array of length n, define the prefix sum p of j as the sum from k equals 0 to j of k. Also define p of negative 1 equals 0 for convenience. If p of j equals p of I, with I less than j, then the sum from I plus 1 to j is 0. Visual proof in one line. Since p of j equals p of I, then p of j minus p of I equals 0. But p of j minus p of I equals the sum from I plus 1 to j of k. Therefore, that subarray sums to 0. Algorithm: scan left to right and maintain the earliest index for each prefix value in a hash map. Seed the map with prefix 0 at index -1, so that a 0 prefix at j means subarray 0 through j is 0. On each step, update the running prefix. If the prefix has been seen before, the earliest index where the prefix repeats is found, and we stop with that earliest j. Otherwise, record the prefix with its index if not recorded yet. Example 1. Consider the array 3, -2, -1, 4, -4, 2. We will scan, build the prefix, and detect the earliest repeat. Initialize the map with 0 maps to -1, then iterate j equals 0 to 5, and update the prefix. At j equals 0, add 3. The prefix is 3, not seen before, so store 3 maps to 0. At j equals 1, add -2. The prefix is 1, not seen, store 1 maps to 1. At j equals 2, add -1. The prefix is 0, already in the map at index -1. We just found the earliest repeat, at j equals 2. The zero-sum subarray is from index 0 to index 2. Graph picture: plot index j on the horizontal axis and prefix p of j on the vertical axis. Equal heights mean equal prefix values. When the path returns to a previous height, the subarray between those indices sums to 0. Why earliest end index? Because we stop at the first j where the prefix repeats. No smaller j can work, so we obtain the earliest finishing index of any zero-sum subarray. The start is one more than the stored earliest index where that prefix first appeared. 64-bit overflow. On machines with signed 64-bit integers, values must remain within -2 to the 63 up to 2 to the 63 minus 1. Prefix sums can exceed this even when answers exist. The safe strategies are: use arbitrary precision integers, or widen to 128-bit, or detect overflow on addition and handle it before it happens. Remedies: 1. Languages with big integers like Python handle this automatically. 2. In C++, accumulate in 128-bit and store keys as 128-bit. 3. If you must remain at 64 bits, check for overflow before s plus equals of j, and stop or escalate to a wider type. Schematic with guarded addition: the new sum equals old sum plus O of j, but only after we confirm it remains within the valid bounds. If it would overflow, widen the type. Example 2. 1, 2, -3, 3, -3, 1. Prefix path hits 0 at j equals 2, and though it repeats at later indices, the earliest repeat happens at j equals 2, so the earliest zero-sum subarray ends at 2. Complexity and correctness: we do a single pass, and each prefix is inserted or checked once, so the time is linear in n. The memory is at most the number of distinct prefix sums seen, which is upper bounded by n plus 1. Correctness follows from the equality of prefix values, implying zero-sum in between. Takeaway: track earliest index of each prefix. The first time the prefix repeats, you have found the earliest ending 0-sum subarray. Guard the addition to avoid 64-bit overflow, or use a wider integer type.